we have one last concept we're going to talk about in this section, which we've kind of indirectly talked about a little bit. And the concept is relative velocity. When we talk about relative velocity, we mean how fast is one object moving in relation to another object that is moving. So for example, when we were talking projectile motion, we had a question where we had an airplane traveling at a constant speed that drops a package from it, a box. I think we did the example on a glacier, a package of food. So if we drop a box or this package, the box initially will have the same speed, but because of gravity is going to cause it to start falling, of course. So it will have a vertical velocity as well as maintain that same horizontal velocity as the plane. It will go, let me draw that. It will have fallen even farther. It will still be traveling horizontally the same as the plane, but will be traveling faster and faster downwards as it continues falling to the ground. So relative to the plane, the package or box that was dropped stays underneath the plane. And again, we're making that crazy assumption of no air resistance. So the package or box will stay underneath the plane, but gets farther and farther below it. So for someone sitting in the plane, watching the box fall towards the ground, to them, it would be the same as if they were in a helicopter, just hovering in place, watching the box fall to the ground. They see the box under them the whole time, but it will get farther and farther away. So what we mean by relative velocity is simply where does this package look like it is compared to where we are in another moving frame. Okay. Now, granted, if the plane, let's say we had a plane, so view from the top, from above, if we had a plane moving in a circle, its velocity at any given moment would be tangent to the circle. So a plane moving in a circle. If a package or box, say at this moment in time, the box was dropped, well, the box would have that initial velocity, for sure. But now that it's no longer in the plane, it's going to continue moving horizontally in a straight line and towards the ground. So if we were in the plane, and in the plane we're now over here, we certainly do not see the box directly below us. We see it over here somewhere. It's definitely farther below us, but it's also moving in a different direction. So relative velocity is just a way of talking about how one object appears to be moving because we, the observer, the one watching, is in a different reference frame. All right, so for now, any type of problem we look at will be very basic. So for example, let's say we are watching a bus drive down the street. So like elementary school kid bus. And the bus is traveling, say, 10 meters per second at this time we're looking at it. And some kids, and yes, my artistic abilities are terribly lacking. Let's say they're tossing a ball to each other. So if a child, one of these kids, throws a ball at 2 meters per second towards their friend, of course the kids see the ball moving at 2 meters per second. But if we are sitting out here watching, so we're the observer, we're watching this happen, how fast do we see the ball going? How fast does it appear to be going from our point of view? Well, we would see the ball traveling at 2 meters per second from the throw, so V of the throw, plus V of the bus. The ball is originally in a child's hand, and so it's traveling just as fast as the bus is. And so the bus and the throw together, as this outside observer, we would say, hey, that ball is traveling at 12 meters per second. But again, that's just because we're accounting for both the fact that the ball has the bus's velocity as well as having the velocity gained from the child throwing it. If this friend caught the ball and was throwing it back at 2 meters per second, we would not see the ball traveling at 12 meters per second. If the kid is throwing the ball to the left, but the ball is headed to the right, we're still going to say the speed we see is the V of the throw plus the V of the bus. But we have to account that the one child throws it to the left while the bus as a whole is moving to the right. So from our vantage point, the ball would be traveling at 8 meters per second. So it's all based on our vantage point, how we are looking at the system. If you've ever ridden the moving sidewalks at the airport, it's kind of fun to walk on those, in my opinion, because I feel like I'm a really super speedy walker because I have my walking speed and the speed of the moving sidewalk that helps me go faster. So this is what we're talking about. On that case of the moving sidewalk, my speed relative to the ground would be the speed of my walking, just in general, by itself, plus the speed of the moving sidewalk. When I move in the same direction as the moving sidewalk, I move much faster relative to the ground. Okay. So one other example here. We have Mary rowing her boat. She needs to row her boat across a 150-meter wide river. And here's the water, here's the ground, here's the ground. We know the river, it tells us the river itself. I'll draw that better. V of the river is east at 1.2 meters per second. That means if Mary just flat out sits in her rowboat in the water, she's going to be traveling 1.2 meters per second east. But of course, she doesn't want to just go east. She wants to make it across the river. Mary can row with a speed of 3.5 meters per second. V of Mary is 3.5, and technically she can row in any direction she wants. If she is in her rowboat and she decides to row her boat east, her speed towards the east would be 3.5 plus 1.2. So she would be going much faster down the river. That's along the lines of walking on the moving sidewalk. But of course, she's not going to be able to cross the river that way. So ultimately, it wants to know how fast is she moving according to someone standing on the shore. So ultimately, we want to say the velocity, accounting for a specific direction as well as how fast, of the river plus v of Mary, those velocity, will be the velocity seen by person on the shore. Now, there's two ways to go about this. The problem doesn't specifically tell us what direction Mary is rowing in. So there's two options here. Mary could technically be rowing such that she's giving herself a velocity directly north, directly towards the other shore. So we would say v of the river, 1.2 east, plus v of Mary, 3.5 north. This would be the velocity seen. The question is asking simply how fast is she moving? So we can just solve for the magnitude, which is the Pythagorean theorem. So we would see Mary traveling faster because she's rowing and the river's helping to move her. And so overall, she's moving at 3.7 meters per second. So this is if she rows north, directly across the river. The other option, though, if she's trying to move directly north, meaning she's not rowing north, she's rowing in a direction to actually travel north, meaning the velocity seen by a person standing on the edge is directly north. So the person is seeing her row directly across the river. Well, we know the river is to the right. If we think about adding vectors head to tail, so for example, over to the right, we drew in the river, and where we ended the river, we draw Mary's velocity, and then the arrow that connects the two was what was seen. Here's our river. Right where we just ended drawing the river, I need to draw an arrow that connects to the top of that velocity seen, because that is the result of adding the two vectors together. So v of the river, v of Mary needs to be in this direction in order for v of the river plus v of Mary to point directly north. We still just care about how fast this is. So we need to find the length of this side, knowing this side is 1.2 and this side is 3.5. We know the river is traveling at 1.2 meters per second. We know Mary can row at 3.5. So Pythagorean theorem still applies here, but we don't know one of the sides. We know the hypotenuse. So we can say 3.5 squared, the hypotenuse squared, is equal to 1.2 squared plus this speed we're looking for squared. Okay. So we can solve for this v. Take the 1.2 squared to the other side, square root it, and I get 3.3 meters per second. The person standing on the shore sees her going a little slower because part of her rowing is combating the river. The rest of it is getting her across the river. So in this particular case, if this was an actual question, so like I said, there's two ways to interpret this. If there were ever a question, say on the test, if you just told me how you were interpreting, that would be fine. Okay? I would technically interpret this the second way, in that she's trying to move directly across the river. Just by how that is worded. She needs to row her boat across the river, and so I'm assuming she needs to head north. And so my assumption would be the approach in this second case, though technically she could be headed across the river, but end up downstream. So in the first case, she would end up some distance down the shore, which is fine. We could figure that out from knowing the river is 100 meters wide. But in this case, I would assume what we solved second. But if this were a test problem, for example, and you explained how you were interpreting it, I would accept your answer as well. But you need to be clear in terms of your interpretation. I totally try not to give you ambiguous questions, though, on the test, so that you don't have to try to interpret what is meant. So this is the last concept in this section. You'll see that the chapter talks about circular motion. We're not going to talk about any of the equations related to circular motion yet. We'll do that when we actually start talking more about circular motion. But I do expect you to understand that something moving in a circle, its velocity is changing simply because the direction's changing. And thus it is accelerating in some way. So I'll make a review video as well for your first exam.